Alrighty, welcome back. Whoa, that's loud. All right, welcome back to operating system. So, more page tables, more virtual memory today because that was fun, right? All right. So, to start, questions. Questions, or was everything slightly comprehensible last time? Yeah. So how it will work is you'll have like a root page table that's set for a process to tell you which L2 page table to use, right? And then knowing which L2 page table to use, you will know which entry to pick from the virtual address. So we get the index from those 9 bits there, right? To tell us which entry to use. And then here, what we had before, the page table entry will tell us what physical page to go to. And before, when we had a single page table, that was just exactly what this virtual page got mapped to. But in this scheme, that physical page tells us what L1 page table to use. So it tells us where this is in memory. So as soon as we know where that is in memory, we know what entry to pick based off this index. And then that tells us where in physical memory the L0 page table is. And then we use that and we get the entry from this index. And then that gives us our final translation. So we would have, so the most number of things, so we'll have that example today is we'll have at most one L1 page table. And if that was full of entries, it could point to 512 different L1 page tables, right? If it was full, and then each of those L1 page tables, if they were full, could point to up to 512 different L1 page tables. And then all the L1 page tables would store all the entries among them. And I would need like a gigabyte of them for every entry because I can't get around that, right? Yeah, so we'll have some more examples today to clarify that. Yep.
So last time we talked about, like one of the trade-offs to using the multi-level page table is at the minimum, you only require 12, 13 kilobytes. It's like one L2 page, one L1 page, and one L0 page.
Yes.
And let's say if I were to allocate another byte, is it possible for the operating system to, rather than reusing the same pages, go ahead and allocate a new L1 and L0, and then that's kind of like, it would be a kind of waste of space, but it can do that, right?
Yeah, so we'll have an example. That'll be my first example to try and nail this down. But that's a good question. All right, any other things of this before we'll try and nail it down a bit more? Okay then. So one quick aside, talking about alignment, you might not have heard this term before, but all alignment is that eventually memory lines up with byte 0. So the reason why we don't have to store the address of, the whole page table is because everything is page aligned. Everything is aligned every 4096 bytes. So that means they all start when all of the lower 12 bits are 0. So in memory, all the page tables would be either start at 0, 4096, 8192, whatever. It would be a multiple of that page size. So if for some reason we had a weird system where like you had to keep track of the whole address, and the page can start at any old random address. So if a page started at like 7C000, so the last 3 hex digits here are not all 0, then the last byte, if you just add 4095 to it, the address of the last byte would be like 8BFF, which would be weird, but because everything is page aligned, we know that, if we get the physical page number 7, well, because everything is aligned to a page, we know that that page starts at the address 7000, so 7000, because it needs to be a multiple of that, and it would end at 7FFFF. So it essentially goes through every single option of all those 12 bits while keeping the beginning part the same. So is that okay? So alignment, you might have heard the term scary, but basically it just means that the address is divisible by that number. So for a question for you, so is the address EC 8-byte aligned? So is this number divisible by 8? Yeah. Yes. So why is it divisible by 8? Because it's 2 bytes. No, like the address. So is this address 8-bit aligned? So is the address itself a multiple of 8? It's not, right? So easy way to check. So this would not be 8-byte aligned. This, again, is the address, not the value. And if it's 8-byte aligned, it means the address is a multiple of 8. Easy way to check is, well, since we're dealing with powers of 2, like this hex digit doesn't matter. We only need to check the bottom one to see if it is a multiple of 8. Because of its powers of 2, we don't have to check the rest of them. So the addresses that are 8-byte aligned, really easy to check. They'll either end with a 0 or an 8. So 0, 8 are the only 2 options, and then those are the only 2 ways we will be 8-byte aligned. So everyone okay with alignment, and that's why we don't have to store the entire address of a page, just the PPN, and we know it always starts at offset 0 and goes all the way to all 1s. So everyone okay? All right. So we simulated an MMU. Any questions about that, or just leave it to go back to a while? So just as a refresher, this is what we had where I set up a whole bunch of page tables. So I set up one L1, one L2, one L1, one L0, and then set their indexes to point to each other in such a way that this address would actually translate. So this MMU function just takes the virtual address, uses the page table starting at the root page table here, follows all the indexes, and tries to translate this address for us. And if it fails at any step along the way, it will generate a page fault, aka your translation is not valid. So anything else we want to play with here, or we want to go back to it at the end? No opinions. All right, so I will leave this in my back pocket then, and if we have time, we can go back. So here's a question for you. So how many page tables do we need? So let's assume our program is actually using 512 virtual pages. Well, what is the minimum amount of page tables I need to actually be able to translate every single one of those 512 pages? And what is the maximum number of page tables and why? So let's go here. So hopefully I fix the iPad thing. So process uses 512 page tables. So the first question was minimum number of page tables. So anyone want to take a stab at this? So remember that a single page table, assuming all my entries fit on a page, that means I have, whoops, I shouldn't have erased that. That means each smaller page table has 2 to the 9 entries. And then I have a 2 to the 3 page table entry size, which means the total size of my page table fits on a page, so it is 2 to the 12. So, assuming my process uses 512 page tables, what is the maximum number of page tables I need? Or minimum number of page tables? Not 1 yet. Is it 2? 2? Not quite. 3. All right, we just went 1, 2, 3. What about if I said no to 3? Someone's going to say 4, and then 5, and then 6. All right, why 3?
I'm assuming that you need L2 to point to L1, L1 to point to L0, and L0 points to 512 pages.
Yeah, so at minimum, you always need at least one L2 page table, right? You just need one. In this case, the minimum number of page tables is it just points to a single L2 entry, or L1 entry. And then that L1 entry points to a single L0 page table. And then that L0 page table, it's full. So it can fit up to 512 different entries. So it is full. It's telling us which pages like to actually translate for each address here. So we have 512. So minimum, we need one of these, and one of these. So 1, 1, 1. All right, everyone okay with that? Yeah.
Is there a reason why we always have to have like those in two steps, like the L2 to L1 to L0?
So is there a reason we have those steps? And the reason for that, like, why do we even use the scheme in the whole first place? Mostly to save memory, right? We had the problem where if we had to translate up to 2 to the 27 different pages, it would mean our page table is 1 gigabyte, even if our process doesn't use that much memory. So the main reason we use this is to just save memory for processes that don't need that many translations. So if you only need to translate a single address, we only need to have 3 page tables here. One for L2, one for L1, one for L0.
So we keep it at 3, like so it has like the capacity to read what we want, like the maximum?
Yeah, so it could have capacity if they were all full. It would be able to do all the translations, but typically you don't need all of them. So most of them would probably be empty. Yeah, so like in this case, oh yeah.
But I follow up that. We always assume we have 27 bits for pointing in the system, so 9 bits for each. Even if the pages are empty, right now we're working with systems which point to 3 pages.
Yeah, so this one is 3, and the reason it is 3 is because, well, we'll have some other problems where we actually calculate the number of levels we need, but in this case, right, I have 27, and then if I make each one fit on a page, I can only fit up to 2 to the 9 at each level. But we can play around with the numbers, and it depends on the system. Oops, wrong thing. All right, so the second question. Whoops. Yeah, we can keep it blue. Maximum. All right, what is the maximum number of page tables? So my process is using 512 pages. Worst case, if I have to translate 512 pages, how many page tables do I actually need to do this? 1025, correct. Everyone know how we got that? No, okay. So the reason why worst case we need 1025 is, well, we need one L2 page table, right? We always need one L2 page table, no way around that one. So everyone okay with that? All right, so if we got insanely unlucky, this L2 page table would have 512 entries all full, and all of them would point to a separate L1 page table. So we would have up to right, everyone okay with that? So it's just full. It's pointing to each entry is full. Each L2 entry is pointing to a different L1. So everyone okay with that? All right, so this is where we get unlucky is the L1s would point to an L0, but if we are unlucky, each L1 page table only has a single entry that points to an L0 page table. So each of my 512 L1 page tables, each only have a single entry that point to a different L1 page table in the worst case, which means I also have 512 L0 page tables. So in total, right, I would need this many page tables in order to translate 512 pages. So that's 1025. So everyone okay with that? Also, you can look at this too. So if you use memory, everyone's told you to use addresses like contiguously, right? But we now know that the virtual addresses you use have no relation to physical, so they kind of lied to you a little bit, right? Why do they tell you to use things contiguously? So remember the index we use for the L0 page table? That comes from the lower bits. So if you're using contiguous addresses, all the entries will be beside each other in the same L0 page table, and you won't need to have more tables allocated for your program and so on and so forth. And we'll see later how we make it faster, but having less page tables, always good. So that's a good reason to always use contiguous memory and so on and so forth. We'll see other reasons, but that kind of makes sense to everyone. So if we used really bad addresses, then our layout would look like this to translate 512 pages. If we were smart about it, we only need 3 page tables to translate 512 different pages worth of memory. Questions? Yeah?
I don't know if this is a silly question, but wouldn't the maximum number of L0 tables possibly be like if every entry in L1 pointed to another L0? So that creates like 512 times 512?
No, so in this one, we're only assuming we can translate. We only need to translate 512 in total. But yeah, you're right that if I need to translate more, all the L1 tables could be full, and then they could all point to different L0 page tables, and then, you eventually get up to like a gigabyte because you need an entry for every single virtual page. All right. Okay-ish. Virtual memory is the best, isn't it? Yeah.
Are we assuming that like all the other entries in the L1 page table are empty and only one entry is valid that's pointing to L0?
In L1?
Yeah.
Yeah, in L1, worst case, each of them has one valid entry that just points to an L0.
And the others are empty?
Yeah, and all the others are empty. They don't point to anything. So if you tried to access that memory, you get a page fault. You can't access that memory. All right, we can do another question then for the other comment for figuring out how many different levels we need. So I can change all of the variables. I can change how many bits we use for virtual addresses. I can change the page table entry size. I can change the page size, whatever. You just have to adapt and kind of know all of the rules. So let's say we assume we have a 32-bit virtual address. So I'm actually, wait, exactly how young are you guys? Have you grown up with 32-bit CPUs? No. Shit. No, I guess, yeah, that was like early 2000s. All right, so this is going back to the days before you were born in the Stone Ages when we had 32-bit computers instead of your newfangled 64-bit that have been around longer than you have. So back in the day, we had a 32-bit virtual address, and our page size was still 4 kilobytes, believe it or not, which I'll also write in powers of 2, so that's 2 to the 12. So this is our page size. So back then, we didn't have as much memory as you people had, so our page table entry could be a lot smaller because, well, we didn't need to support a bigger physical page number, so we could actually, instead of having an 8-byte page table entry size, we had a 4-byte. So that is 2 to the 2, and that is my PTE size. All right, so now we should be able to figure out how this system works and how many levels of page tables we actually needed. So the first thing you want to figure out is how many entries, well, let's call them PTEs per, and see, I can actually write on my iPad now. It's so much better. My writing should have improved slightly. Okay, camera, please come back. So first one, how do I figure out how many page table entries I can fit on a single page? Yeah?
You take 2 to the power of 12 divided by 2 to the power of 2, so you need 2 to the 10 PTs.
Yeah, so I take the page size to the 12, that's as big as my page is, and then I need to figure out how many page table entries I can fit, so I just divide by 2 to the 2, which gives me exponent law, 2 to the 12 minus 2 is equal to 2 to the 10, and just in case I need it, I don't actually need it for this. Keeping in powers of 2 will probably be easier, but that is 1024, which makes sense. Same page table size now, but nowadays we can only fit 512 entries, but if you half the actual size of the page table entries, it makes sense that you could store twice as many. So, is that okay with everyone? All right, so remember how our virtual address is laid out. So our virtual address how it's always laid out is we take the big VPN and we would divide it into number of levels, and then we also have an offset that, let's do it at the bottom. So we would have our offset here. How many bits do I need for my offset in this system? 12, right? So it's just I have to be able to address every byte on the page. So if my page size is 2 to the 12, that means I need 12 bits to tell me which byte on the page I'm trying to access. So this was too bold. So this was 12 bits, right? And then for all of my indexes, right? How many bits did I need for my index? How many bits do I need for an index in this scenario? AKA, I must be able to access every single entry on the page table. Yeah, 10, right? So in general, you can call them, so here is like, the general word to call them is how many index bits you need. In this case, in this system, I need 10, right? So the general formula to figure out how many levels of page tables I need is just the number of levels I need is equal to ceiling, number of virtual bits, minus offset bits, divided by the number of index bits. And it's ceiling because even if my entry will not be full, I need at least another page. I need at least another level in order to translate everything. So in this scenario, my number of virtual bits was 32 minus 12 offset, which basically, if you wanted to shortcut it, it's just how many bits are used for my VPN. So in this case, it would be 20. And then it's just all divided by the number of index bits, which is how many entries we can pack on a single page. So in this case, it is 10. And then it would be ceiling. So if we crunch these numbers, it's just 20 divided by 10 ceiling, which equals just 2. So I would need, in this scenario, an L0 index and then an L1 index. So I only need 2 levels of page tables. Yeah?
So for this case, there would be no unused bits, right?
Yeah, for this case, there would be no unused bits. But as soon as I said, hey, let's, I don't know, let's do a 33-bit virtual address, well, then suddenly I need another page table. I need an L0 page table, but that would only have 2 different entries, right? So kind of a waste. We kind of want them to be full. But if your number doesn't divide evenly, then that's why we take the ceiling here, because we can't have half a page table or something like that. All right, cool. Any questions about that? So back in the day, so 32-bit CPUs, this is what we used, 2 levels of page table. And then 64-bit came along, and even with the 39-bit virtual address, how many levels of page tables did you need? Cough. 3. And what is the consequence of that? More indirections, aka it was slower, right? So every time I have to translate an address, I have to go through another memory access. If I'm using a 64-bit address, even with only 39 virtual bits, as opposed to a 32-bit machine, that only needed 2 levels. So, history lesson, when people first started transitioning to 64-bit, there was a big reluctance because it was slower and people didn't have so 32 bits covers up to 4 gigs of RAM. People didn't have that much RAM. And you just upgrade to a 64-bit processor and it's slower. So you're just like, wow, this 64-bit thing is sure not going to catch on because who needs more than 4 gigs of RAM, right? Yeah. So initial reluctance, but we got used to it. All right, another thing we have to address is, yeah, using page tables for every memory access is slow. I'm following pointers across multiple levels of page table. So every memory access, if I have 3 levels of page table, every memory access turns into 4 because I have to go from find the L2 entry, then find the L1 entry, then find the L0 entry, and then finally do my memory access. So this is really, really slow, and it is likely you will access the same page multiple times, especially if you're accessing an array or something like that. So a process might actually not use that many pages at any given time. So it only needs a few like virtual page number to PPN mappings. So the solution is one of like the two computer science solutions. If something is slow, you add a cache. So the cache for translating virtual addresses is something called the TLB, or the translation look-aside buffer. So this is one of the terms you will definitely have to commit to memory, because you can't pass this course without knowing what a TLB is. So TLB, what it is, it's basically just a cache for looking up the VPN translations. So how that works is we have our same virtual address before, same 39 virtual bits for the address. Again, we don't have to translate the offset. And instead of doing that big, slow process every single time, well, what your computer do, there's hardware for this, so it will actually have a table of VPNs to page table entries that were the entries in the L0 page table. So the final page table entry you actually wanted to compute. So what it will do is, instead of going through that whole process of looking it up, it will check if it already exists in the cache, aka that old result was saved. And if that old result was saved, it doesn't have to go through that whole rigmarole. It doesn't have to go through that whole process. It can just get the PPN from the page table entry, and then we immediately get our physical address. If it is not in this table, well, then it's called a TLB miss. It's not in the cache. We have to go through and translate using page tables. So this will go through that whole process we just went through of L1 pointing, or L2 pointing to L1, pointing to L0, and then finally getting the page and finally getting the PPN. But how your hardware actually works is, after it's done that translation, it will actually add the entry to the TLB to save it for later if you try and access the same memory, and then it would give you this physical address. So everyone okay with that? So just saving our results so we don't have to do this slow thing. And turns out, oh yeah?
Question, how is it different from just having one big page table? If we are ultimately adding all of the correlations, all the lookups to one big cache?
So this cache has a set size. So it can only store a few different translations. So yeah, it won't fill up the whole thing. But yeah, it'll be small enough, and then you'll go into cache policies and stuff of like what I throw out in some other courses, but that will only be able to handle a few different translations at a time. Yeah?
Wait, so it checks all 27 of the VPN and see if it matches?
Yeah. Yeah, so it checks if this VPN was already translated. If it was already translated recently, it'll just use that result.
And then it gives you the physical page.
Yeah. Yeah, so it would just save the result of the translation, like the last step it needed. And then that's it. So caches, basically, we're just saving our results so we don't have to recompute it over and over again. Yeah?
So is the cache actually saving the L0?
Yeah, it would save the final translation. So yeah, it would save like the L0 entry. So like,
Entire L0 page?
no, just the L0 page table entry.
Okay.
So like, what physical page should this VPN map to?
So in this case, having contiguous addresses doesn't actually make things better?
Yeah, contiguous addresses would not help for this at all. Yeah. Yeah.
So because virtual page numbers are process isolated, I would assume you'd have TLB per process as well.
Yeah, so this TLB would be valid per process. We'll get into that a little bit too, but that's a good point, because these page tables are only valid for processes, right? So just because one process uses address 1,000, doesn't mean it's going to have the same physical memory as another process using that same virtual address. Yeah?
Sorry, but this is a like actual piece of hardware I'm looking here? Or
Yeah, this is actual hardware on your CPU.
But there's multiple depending on the process? Or?
No, so there's only one TLB, and it only is valid for a process because that's your translation. So we'll see in a second what we do. Because yeah, we have to be careful. We can't use that for a different process, right? Because their mappings won't be the same as our mappings. So we have to do something about that. But I like the question, but we will see it. All right, actually, I think it's the next slide. Oh, wait. Okay, first slide. Next slide, just to show that we get good performance and it is close to using physical memory, is assuming we only have a single page table, there's only one additional memory access. So again, if we use 3 levels of page table, there would be 4 different memory accesses. Know that point because that might be asked of you. So if we were to calculate what our effective access time is, aka what is the average time spent to actually access memory, well, we can take our TLB hit time. So it takes a little bit to search if this entry is valid, if it's in the cache. So that will be typically pretty fast, but not negligible. So there'll be some TLB search time. And then that would tell us the physical address to use, and we can just do our normal memory access. So if there's a hit, we basically add a little bit of extra time as opposed to just using raw physical memory. If there is a miss, then we still have to search the TLB, and then it would not find it. And then we have to do as memory accesses as we need to be able to translate this and then do the original memory access. So for a single page table, this would be 2 memory accesses to find, 1 to find the entry, 1 for the final access. If this was a 3-level page table, then this number would be 4. I have to access a L2 entry, an L1 entry, an L0 entry, and then the original memory access. But other than that, it is simple math. So the effective access time is just alpha, aka the hit rate. So how often is an entry in the cache, times the hit time, which is just this number, plus the miss rate, so it's just 1 minus alpha, times however long it takes for a miss. So for instance, if you hit 80% of the time and it takes 10 nanoseconds to actually to search the TLB, and normal memory accesses take 100 nanoseconds, our effective access time would just be 80% of the time we have to search and then do the memory access. So 80% of the time it takes 110 nanoseconds. And then 20% of the time it takes 210 nanoseconds. So I have to search the TLB and then find the entry and then do the original memory access. So the effective access time in this case would be 130, which means it's only 30% slower than just using physical memory. So not as bad, and in the real world, your hit proportion would be slightly higher than that. But does that make sense? A little calculation there. So that big cache is how we get performance close to actual physical memory. So we can actually experiment with this a little. Oh, and here's the other point you brought up. Yeah, so if I context switch between processes, each process has its own page tables because it has its own virtual memory. So whenever I context switch, we now know another piece of the puzzle. It would need to switch which page tables it's using, along with switching all the other registers. So the options are you flush the cache, which means just clear it. So that TLB that stored all the mappings, if I switch to a different process, which has different mappings, I just have to clear all the entries because they are no longer valid. Otherwise, I would maybe accidentally use another process's memory. Or what you could also do, another option is you can have hardware support. So you can actually attach a process ID to TLB entry to say that this translation is only valid for this process. And at a hardware level, it will not translate it if you're trying to access it with a different process. Most implementations, that hardware support for attaching process IDs most of the time doesn't exist. So most implementations of the kernel, whenever they switch to a different process, they just flush the TLB. If you're using RISC-V, there's a special instruction to do that. sfence.vma, so something to do with virtual memory. On x86, so most Windows laptops, whenever you change that register that tells you what base page table to use, that at a hardware level immediately flushes the TLB for you. So if you change the root page table, it will flush the TLB for you at a hardware level. So if this didn't happen, bad things would occur. All right, everyone all right with that? Hopefully that addressed the other concern. All right, so we can actually try this out. So there is some fun code that was written, not by me, but to show the effect of the TLB. We have this little program called test-TLB, which is, funnily enough, written by the same guy that wrote the Linux kernel. So this program is very, very simple. This program takes two different command line arguments. The first argument is the size. So that will actually allocate that many bytes of memory for you to use. And then this stride just means it will access every stride byte. So if the stride is 4, it will access every 4 bytes. So if I run this, let's see, 4. So if I run this with this argument, it means I will make an allocation for 4096, which is the size of a page, and I'm going to access every 4 bytes. So if I do that, how many TLB hits will I have and how many misses will I have? Yeah.
Will you miss one and hit 2 to the 10 minus 1?
Miss once and hit to the 10 minus 1. To the 10? Yes. So what this will do, it will allocate a page and then access every 4 bytes. So like byte 0, 4, 8, 16, blah, blah, blah. And that would do in total 1,024 accesses. The first access, right, it's accessing new memory. It wouldn't know the translation for that. So it would need to figure out, hey, this virtual page, what physical page does this map to? It would have to do all the translation, but then it would save that result in the TLB or the cache. And every single memory access would also be to this page. So it would be essentially one miss. We populate the TLB, and then we have 1,023 hits all in a row, right? So if we do this, run this, we see it's fast, like 1.3 nanoseconds, something like that. Other extreme. What if we do something like, whoops, do I have the number? What about if we do something like this? So bottom right corner there, this allocates 512 megabytes of memory, I believe. And then we access every 4096th byte. So byte 0, byte 4096, so on and so forth. So how many misses do I get in this scenario? Yeah.
Whichever the division result is.
Yeah, every time, right? Every single one would be a miss. So I'm guaranteed to access a new page every single time, right? So if I run this, I will see it is way slower. So from 1 nanosecond all the way up to 30. So I went 30 times slower because I was accessing a new page every single time. And now we know that, well, it had to do the translation every single access, and it is hella slow. Yeah?
Does it just like save, it just saves the page that you use and assumes it'll go back to it, type of thing?
Ye-
I don't know what to save.
So it just saves the result of whatever address you used. So in the first case, the first access, it would do the translation, save the result, and then it would be able to reuse it again and again and again. If I do this memory access where I access a new page every time, every time I access a new page, it would save the result, but it wouldn't use it because next access I use a different page. And then a new page, and then a new page, and a new page. And then turns out caches are good because this is 30 times slower. So the main reason they tell you to use memory contiguously doesn't have to do with computers just like bytes all in a row. Did anyone ever, like, that didn't sit well with them? Like, we have to access things contiguously, they're all in a row, and that seems weird when I'm accessing, like I'm using something called RAM, random access memory, where all the accesses should take the same amount of time, so why do they all have to be in a row? Now we know the answer, it has to do with pages. So the reason why is if you access things contiguously, it's more likely they'll all be on the same page, and it'll be really, really fast. Because those pages in physical memory, they can be random, they don't need to be anywhere near each other, right? So they have lied to you all these years. This is why you want to access memory contiguously. You can actually explain that to people now. Yay, we know stuff. Ish. All right, so other little things. So that SBRK for user space allocation that resizes a heap, right? That was a system call we saw libc use. That's what malloc uses. And they'll grow or shrink your heap. And how it works at the kernel level. For growing, all it does is like grab more pages from the free list to fulfill that request. And the kernel can just set up the page table so that it has valid entries that point to those new pages it gets, and whatever other permissions, read, write, things like that. Memory allocators are also fairly difficult to use. Most of the time you'll rarely shrink the heap, and that's why your process, even though it might not be using that much memory at a given time, it's generally hard for them to free the heap because malloc's the thing that's managing the heap, and it can only shrink it if like pages are unused at a time, and it has to be like the last page it has. So most memory allocators will actually waste a bit of memory. They actually use a system call called mmap, we'll see a bit later, to map large blocks of virtual memory. That's a system call where you can try and manage your own virtual memory. So big diagram, this is how the virtual memory is typically organized in your process. So your process, usually everyone's dereferenced null. So the reason that works is virtual page 0 is always mapped as invalid. So that doesn't, there are systems, if it did have a mapping for it, whenever you dereference null, you wouldn't get a page fault or a seg fault or anything, you would get valid memory. That's something they could do, but they were like, hey, no, we want it to page fault immediately, so virtual page 0 is always invalid. And then above that, you know, based off the program we're loaded in, maybe we'd have these pages for instruction, these pages for data, and then we have a stack. All your stacks are a set size, they have a set limit, and how the kernel detect, or how you detect stack overflow errors is, well, your stack's going to be a set size, and then what they do is put something called a guard page at the end of the stack, so that if you overfill your stack, instead of just getting seg fault, and that doesn't help you at all, it's a known page, so you will get, if it sees a page fault on this page, it knows it is likely you have overfilled your stack, so you'll get a stack overflow error instead of a page fault. So I don't know if some of you have encountered this. Have any of you encountered, you know you have a stack overflow, but you don't see stack overflow? So if you have encountered that, that means you have overflowed your stack to such a degree that you jumped over this guard page. So if you overfill your stack by over a page, you will probably jump over the guard page, and then it will just tell you seg fault, not stack overflow anymore. So if you really screw up, you won't see that anymore. And then the heap, and then there's some additional instructions which has to do with context switching, because the kernel would have its own virtual addresses, but we can ignore that for now. So another thing the kernel can do is provide fixed virtual addresses for your program in order to avoid system calls. So if your program knows, it's doing something like reading the time, the kernel can set up a known virtual address so you can just read the time from that virtual address without having to do a system call. So that is the only way to get information from the kernel without actually doing a system call. And we are out of time, so just remember,